So let's go ahead and take a look at our intro problem for Unit 4. Okay, so this says companies from McDonald's to Walmart to probably most restaurants, most retail places, they rely on hourly workers to make food, run cash registers, take care of inventory, all kinds of different stuff. So let's imagine that a business opens in a new city and they want to hire people. Our table here shows us how many people would want to work at 3 different hourly wages. So number of individuals who want this job we'll call our supply, right? Our employees, the people that we need to work at this new business. And then how many the company would be willing to hire at each of those 3 different hourly wages. So that will be our demand, how many employees the company needs. So I want you to notice that as our wage increases, the supply also increases. We have more people interested in having a job that pays $12 an hour versus $3 an hour. But our demand does the opposite. So our company is not willing to hire as many people for $12 an hour as it is for $3 an hour. Okay. So what we want to take a look at here is the relationships. So on the next page, we have those points plotted. So here were the demand points that we had, the number of employees that our company was willing to hire. And I made those one color just so we could kind of differentiate them. And then I just sketched the lines for those points. And that represented our demand. And then our other points, our supply points, I also connected just with a different colored line so we could kind of look at the difference between those two. So we notice our supply line again goes up as that wage increases, but our demand line goes down as the wage increases. We see that? Okay. So the first question that we're looking at here says, if in the United States, the federal minimum wage is $7.25 an hour, and I believe that might be an outdated figure at this point, but it says this is the lowest employer can legally pay its workers each hour. If the company only pays minimum wage, so $7.25 an hour, can it hire as many workers as it wants? So if I go down to the bottom of my graph here, between 6 and 8 would be our 7. This next line here would be 750. So halfway in between there would be our 725. So for 725 an hour, here's that point on my supply line, and here's that point on my demand line. So this is about how many workers our company wants to hire. And then down here, this is how many people want that job. So our company wants to hire a little over 220 people, maybe 225. But I only have maybe 175 people who want that job. So are they going to be able to hire as many people as they want to? No, I have this sort of gap here. Okay. So I'm going to flip away from my graph for just a second so we can kind of jot down our thoughts on number 2. So we know that the answer is no. For a wage of $7.25 per hour, the company would want to hire, I'm going to say approximately, that kind of curvy equal sign means approximately. Approximately, I think we said 225 people. But only, again, we'll say approximately 175 workers would want the job. So we have this kind of mismatch here. might be the ideal case. Yeah, those numbers would match, right? Ideally, this number and this number would be the same. So that's actually what we want to look at. What's the lowest wage at which the restaurant can hire exactly the number of employees that it wants, where I have the same number of people who want the job as they need. So if I flip back to my graph, what would I be looking for on the graph? Exactly right, where those two lines intersect. That point right there where those two intersect. So this is roughly, let's see, there's 850. This is just before 9, so let's say that's 875. And then it looks to me like it's pretty close to halfway between 200 and 220, so we'll say 210, maybe 212. So what that means is that for 875, we have 210 people that the company is willing to hire, but we also have 210 people interested in the job. That's like kind of the sweet spot for this problem. That's what we're looking for. When do those numbers match? If I flip back over here, the lowest wage would be $8.75. And this is the intersection of the supply and demand lines. That's what I want. Where do those two meet? That's the X value there. That wage is going to be the minimum amount I need to offer per hour to make sure I can hire as many employees as I want to. So this is the minimum wage where I'll be able to hire as many people as I want to. What if I bump that up? Let's say we make our minimum wage $15 an hour. So this company is willing to offer $15 an hour. So 15 would be here, halfway between 14 and 16. And there's our point on the company line. There's our number that they want to hire. And then up here is our point on the supply line. So this is how many people want that job. What kind of situation do we have going on here? Exactly right. We have more interest in the job than the company is willing to have for employees. So at $15 per hour, there would be more people interested in the job than the company is willing to hire. So they would have a lot of applicants, but fewer positions available. What we're looking at here is a system of equations. We had multiple lines that we were looking at, right? And we can represent an equation with a line. We had multiple lines we were looking at, and we were looking at how those lines interact with one another. That's a system of equations. Questions for me? Okay. So let's turn to page 129. So again, sort of a more formal definition of our systems of equations. A system of equations is a set of two or more equations. So we're only going to look at sets of two equations, but you could have 3 or 4 or 5 or 17 or 112 equations. We're going to stick to 2. It's a set of 2 more equations where I'm dealing with the same sort of variables. So hourly wage and number of people were our variables for that last problem. Our solution would be, in this case, those values that were on both lines, okay? That intersection point. So from that problem that we just looked at, the intro problem, we had lines that we were basing all of our judgments off of, all of our estimations were based off those lines, but we could actually write equations for them. So just as a sort of a refresher from what we looked at on our last unit, if I want to write an equation for the supply line and for the demand line, we had some points on those lines so we could find their slope and we could write an equation. So I'm going to pick the first 2 points from the supply line. That was 3, 72 and 5, 120. And I'm going to find the slope between those 2 lines. So remember, for slope, x on the bottom, y is on the top. So for my first point, 3 goes on the bottom, 72 goes on the top. For my second point, 5 goes on the bottom, 120 goes on the top. 120 minus 72 gives me 48. 5 minus 3 gives me, 2. 48 divided by 2 gives me 24. So I know the slope. I've got some points. I'm going to write point slope for this line. That would be y equals 24 times x minus 3 plus 72. I just used my first point there. And then I can do the same thing to get an equation for my demand line. The first 2 points, and again, it doesn't matter which 2 points you pick. I'm just picking the first 2. The first 2 points on my demand line were 3, 256 and 5, 240. So I'm going to find my slope. Remember, x goes on the bottom, so 3 on the bottom, 256 on top. And then for my other point, 5 on the bottom, 240 on top. 240 minus 256 would give us negative 16. 5 minus 3 gives us 2. Negative 16 divided by 2 is negative 8. So I've got my slope. I'm going to pick that first point again. I've got a point. I can write point slope form here. So y equals negative 8 times x minus 3 plus 256. So here would be my system of equations. And then my solution is that point where they intersected, okay? That point is on both lines. That makes it my solution for the system. Okay? So my solution was 8.75, 210. Right, that was, I'm going to flip back for just a second. That was the point where our lines intersected, the point that they shared. And in our problem, we talked about how that meant that for 8.75 an hour, there would be 210 people interested in the job. 210 people interested in the job. And the company would be willing to hire 210 employees. So a system of equations and our solution and what that solution means. Questions for me? Okay, so this strategy that we used, looking at an intersection point for two lines, is a system, or is a method, I should say, to solve a system of equations called graphing. So this is using graphing, using a graph to find a solution. We're going to look at several different methods to solve systems of equations. The one we're going to focus on today is graphing, finding those solutions using some graphs. But we'll also talk about some algebraic methods that we can use to solve systems of equations. So we'll get those later. For now, we're going to focus on the graphing. So for my first example down here towards the bottom of page 129, we have two equations and we want to solve our system by graphing. So that means I want to graph each of these lines and look at where they intersect. This first line is in standard form. I'm going to go ahead and change that to slope intercept just to make it a little easier to graph. So I'm going to move this 3x to the other side. So this would become y equals negative 3x plus 9. And then I have slope intercept form, so I'm going to go ahead and graph this. My y-intercept is 9, so that's right up there. And then my slope is negative 3, so that's telling me to go down 3 and over 1. So down 1, 2, 3, over 1. Down 1, 2, 3, over 1. Down 1, 2, 3, over 1. I know some of these are a little tricky to see. Down 1, 2, 3, over 1. 1, 2, 3, over 1. Until I just run out of graph there. And I'll go ahead and connect my points to finish up my line. So there's one equation graphed. Now I'm going to graph the other one. I'm going to use different colors here just to make it a little easier for us to talk about what line we're looking at. You do not have to have like multiple highlighters or colored pens or anything like that. You can just use your pencil for all of them. That's fine. I'm doing it just to make it a little easier for us to talk about and see what's going on up here together. So my second line is already in slope intercept form. My intercept is negative 1. So that would be right here, my y-intercept. And then my slope is negative 1. So that means down 1 over 1. 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 So my solution, again, is where those lines intersect. So that would be right here. We had a point that I plotted for both lines, and that's the point 5, comma, negative 6. So my solution here is the point 5, comma, negative 6. Questions for me on this one? So we're graphing lines and looking at where they intersect. That's our first method for solving. We're going to do a few more examples together. So if you turn the page for me, we're going to look at page 130, and we've got a couple more examples to take a look at. So for example 2, again, I've got two lines. I'm going to graph each of them. So my first line, my y-intercept is at 3, and my slope is negative 2, so down 2 over 1, down 2 over 1, down 2 over 1. I plot as many points as I can. I'm going to trace them back this way as well. This would be up 2, back 1, up 2, back 1. And then for my second equation, again, I'm going to change this to slope-intercept form to make it a little easier to graph. So I'll start by moving x to the other side. That would give me 2y equals x minus 4. And then I want to get y by itself, so I'll divide every term by 2. That would give me y equals 1/2 x minus 2. I have a y-intercept at -2. And my slope is 1/2, so I'm going to go up 1 over 2, up 1 over 2. And at this point, I can see where my solution is going to be. So I'm going to go ahead and stop plotting points there and go ahead and sketch my graph. There's my solution at 2, -1. So over here, I'm just going to label that as my solution. Again, I graphed each line and I looked at where they intersect. Example 3, same idea. We've got 2 lines to graph. So for this first one, my y-intercept is at -1, and my slope is 1/2. So up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, down 1, back 2, down 1, back 2, down 1, back 2, down 1, back 2. For that first line in particular, I try to plot as many points as I can. Since I don't know where that second line is going to fall on my coordinate plane, I want to make sure that I fill as much of that space as I can with it. And then for my second line, again, I want to change this to slope-intercept form. So I'm going to add 3x to both sides. So y equals 6y equals 3x plus 6. And then to get y by itself, I'm going to divide each term by 6. So I get y equals 3 over 6 would be 1/2 x plus 6 over 6 is 1. Now I've got slope-intercept form. I can plot my y-intercept at +1, and my slope is 1/2. So I'm going to go up 1, forward 2, up 1, forward 2, up 1, forward 2, up 1, forward 2, and down 1, back 2, down 1, back 2, down 1, back 2. Oops, I'm up here a little bit. Down 1, back 2. There we go. There we go. There's our green line. What do we notice about these? They're parallel, yeah. What do we know about parallel lines? They never intersect, they never touch. So if our solution to a system of equations is the place where those lines intersect, what would we say about the solution for this thing? There aren't any solutions, yeah. If our solutions are places where our lines cross or touch or intersect, and we have 2 lines that will never intersect, then we have no solution. Questions for me on example 3? Okay. One more I want to look at together for today. For example 4, again, 2 equations. So I'll start by graphing this first one. My y-intercept is at -4. My slope is 2 over 3. So I'll go up 2 over 1, 2, 3. Up 2 over 1, 2, 3. Up 2 over 1, 2, 3 is out here somewhere. and then down 2, back 1, 2, 3, down 2, back 1, 2, 3. And then for my second line, again, I'm going to change this to slope-intercept form. So move that 2x over. I get negative 3y equals negative 2x plus 12. Divide every term by negative 3 so I can get y by itself. So I get y equals negative divided by a negative would be a positive. And then I can't reduce 2 over 3 anymore, so I'll leave it as 2/3 x. 12 divided by negative 3 would be negative 4. So my slope-intercept form for that second line is y equals 2/3 x minus 4. So I'm going to plot my y-intercept of negative 4. And then my slope is 2 over 3. So up 2 over 3, up 2 over 3, up 2 over 3, down 2, back 3, down 2, back 3. What do you notice here? Yeah, my lines are going to completely overlap. Every point on the first line is also on the second line. They're the same thing, right? And I can see that from slope-intercept form. They're identical. I got exactly the same thing. So if my solution to a system of equations are the points that are on both lines, right? Before we saw places where they intersect, that point was on both lines. What would that mean here if every point is on both lines? That means that every point then is a solution. Every point is a solution. So when every point is a solution, we say that there are infinite solutions to this system. There are infinite solutions to this system because every point on the line is also on this line. So every point is the solution. So when we talk about solutions for a system of linear equations, right, when I'm looking at two lines, I've got three different possibilities. I could have one intersection point between those lines. I could have no intersection points between my lines. Or I could have infinitely many intersection points between those lines. Okay? Questions for me for today? Okay, for the rest of our class time, I want you guys to work on your homework and ask questions if you have them. So your homework problems are pages 131 and 132. Doing exactly the same thing that we just did together. So you've got a system of equations. I want you to graph them and then tell me where your solution is. So if you've got one solution, list that point. If you have no solutions, tell me no solutions. If you have the same line that you graphed twice, then tell me infinite solutions. Okay? 131 and 132 for your homework for today.